This presentation will be given in a seminar style, and I assume that you have basic knowledge to understand this presentation from the lecture course given so far. In fact, a part of this presentation has some overlap with the lecture course. So the topic I'm going to tell you here is the application of the entanglement suppression idea for the spin 3/2 baryon scattering systems. So here are the contents of my talk today. So in the former half, I give you an overview of the idea of the entanglement suppression that has been initiated by these papers, taking an example of the two-nucleon scattering. And in the latter half, we present our recent work for the scattering of IC3 baryon decuplet, which has some phenomenological application to the omega-omega scattering. This work has been done in collaboration with the people listed here. Ian Lowe is the high-energy physicist, but he's recently interested in the application of this kind of quantum information science idea to the high-energy physics, and this work is also a part of this kind of program. Fenkun Guo is the world-leading hadron physicist from ITP Beijing. And Taoran Fu is the student of Fenkun at the University of Chinese Academy of Science. And Katsuyoshi Sone is my student at Tokyo Metropolitan University. So the main part is this work, but before I'd like to give you some overview of this entanglement suppression idea, this part. So the more precise definition will be given later, but let me give you some basic concept that we are going to discuss here using the entanglement suppression idea. Now we are considering the hadron scattering, which can be viewed as the S matrix that characterizes the quantum scattering, which changes the initial scattering state to a final scattering state. And we define the so-called entanglement of power of S matrix, that is that quantifies the ability of generating the quantum entanglement through the scattering process. So each state, the initial state and the final state, has some different entanglement structure, and S matrix can change this entangling structure from the initial state to the final state. In some cases, it generates entanglement. In some cases, it reduces some entanglement. And this entanglement power, the quantity, EP, is the some number that is average generation of entanglement from the initial to the final state. Now, the idea of this entanglement suppression is to require the condition that the entanglement power of this particular S matrix should vanish, which give us some constraint on the structure of the scattering S matrix. And the constraint on the scattering S matrix has some consequence on the property of the two-nucleon force, for instance. And that actually explains the so-called emergent symmetries appeared in the phenomenological two-nucleon scattering. This symmetry I will also explain later. But the basic idea is to focusing on the entanglement nature between the initial and the final state. We can talk about the property of some hadron scattering. Now, this was started from the two-nucleon scattering, but later on, there are some applications to, for instance, using other hadron scattering or some free-body nuclei scattering system, and even for some application to the exotic hadrons. There is some recent review article not only covering for this entanglement suppression idea, but also covering some general aspects of this quantum information science in the application of the high energy physics that has been given in this paper. So let me start by reminding you the symmetries of nucleon scattering from the basic fundamental theory of QCD. Now we know that QCD has a spin SU2 and isospin SU2 symmetries, where because of this symmetry, actually this is a symmetry for quarks, which give us some phenomenological consequence in the physics of the hadrons. Namely, hadrons also satisfy this spin SU2 and isospin SU2. In terms of the two nucleon systems, nucleon is a spin 1/2 state. So under the spin SU2, up spin and down spin of the nucleon should be treated on an equal footing. In the same way, the isospin SU2 is the internal degrees of freedom, which characterizes the proton and neutron. And it has been known that the basic nuclear force, the strong interaction between two nucleons, has this approximated isospin symmetry that is actually known to be originated from the isospin symmetry in QCD. So in both cases, these states, the nucleon state forms a spin or isospin 1/2 component. So in order to talk about the two nucleon systems, you have to combine two spin 1/2 state in the tensor product. So in that case, you have in the total spin singlet state or total spin triplet state. And for later convenience, we remind you that the spin singlet is the anti-symmetric under the exchange of two particles, nucleon 1 and nucleon 2, while spin singlet, it is asymmetric. Now, we consider the low energy nucleon-nucleon scattering where the S wave, the angular momentum zero component dominates. And in that case, spin and isospin cannot be freely taken because its combination, in order to have the total two nucleon state to be anti-symmetric under the nature of the Fermi-Dirac statistics, the combination of the spin and isospin should be anti-symmetric. Therefore, if you choose a spin anti-symmetric spin 0, then the isospin must be symmetric, namely you have to combine I equal 1. So J equals 0 and I equal 1 state. Or in nuclear physics, it is called the singlet S0 component is allowed. And also spin 1, if you choose the spin symmetric, then isospin must be anti-symmetric, isospin 0. This combination is known as a triplet S1 component. So the good point of this asymmetry is that there are only two independent degrees of freedom into nucleon scattering at low energy, and therefore you can characterize, for instance, two-phase shift to talk about all possible two nucleon scattering at low energy. But one thing I have to emphasize here is that these two components are actually independent under these symmetries. Independent means that one of the channels can be very strong, one of the channels can be very small, or one channel is attractive, the other channel repulsive. And this kind of the relation between these two interactions are not given, are not constrained from the symmetries in QCD. So this is something we can expect without any calculation, but just from the symmetries of QCD. And of course, it is realized, but in nature, we know that the much larger class of symmetries also realized in the two nucleon scattering. And this we call the emergent symmetry. Now, one thing we can notice is that the scattering length of the two nucleon system, either singlet S0 or triplet S1, the scattering length is much larger than the typical length scale of the hadron interaction, which is of about 1 femtometer. For instance, in the singlet SL case, it is about 20 femtometer, which is much larger one. In the triplet S1 case, it's not as large as the singlet component. It is actually 4 or 5 femtometer, but still it is actually not very same order with this 1 femtometer scale. So we may expect that in both cases we have some large scattering length. And this large scattering length is actually induces a scale invariance theory. And in the non-relativistic system, it is known to exhibit a non-relativistic conformal symmetry. That has been discussed in this paper. But anyway, this large scattering length of appearing into nucleon scattering induces some additional symmetry, which is not existing in the original fundamental theory of QCD. Another one is that we, as I already mentioned, not only one component, but both components have larger scattering lengths compared with the typical scale, which means that two independent channels have actually a similar behavior in terms of this scattering length. And this is actually known as the spin flavor SU4 symmetry that has been discussed by Wigner a long time ago by looking at the structure of a nucleus. More recently, it has been somehow discussed from the viewpoint of the large NCQCD and so on. But essentially, what we consider in the SU4 is not only considering SU2 cross SU2 independently, we consider the all possible spin isospin combination, namely proton up, proton down, neutron up, and neutron down, in the same multiplet or same fundamental representation with SU4, and consider the symmetry under this SU4, which is actually stronger than SU2 cross SU2, and we obtain that the relation between these two, spin singlet and spin triplet, must be the same interaction. That is a consequence of SU4 symmetry. So anyway, of course, this is an approximate symmetries, but in nature we see that some enhanced symmetry or enlarged symmetry appears in the two nucleon sector, and we do not know the reason why this symmetry emerges from the dynamics of the strong interaction. And the entanglement suppression idea is one of the possible explanation of this emergent symmetry, and that I'm going to discuss from this former half of this talk. So to talk about the entanglement, we have to quantify the degree of the entanglement for a single two nucleon state. And there are many entanglement measures, entanglement entropies, or some other quantities that characterizes the entanglement nature of the system. So in general, we consider so-called bipartite state, or in the present case, we have a two particle system, particle A and particle B, both living on some Hilbert space of each component, and the state is given on this Hilbert space. In that case, you can define the von Neumann type entanglement entropy, or some in the present calculation, we utilize a so-called linear entropy. In both cases, we first construct the so-called reduced density matrix rho A, which is given by tracing over the original density matrix of some state that you are interested in, tracing over one of the component, namely in this case, tracing over a particle B. Then you obtain the density matrix acting on the subspace of a particle A. This is called the rho A, or reduced density matrix. And by using this reduced density matrix, you combine this in terms of rho log rho type, like a von Neumann entropy type combination, and taking over a trace of A, then you get some number. And it is known that this quantity characterizes the quantum entanglement between this subspace A and subspace B based on this quantity. Now, in the present case, we actually utilize a so-called linear entropy. Formally, this one can be obtained by expanding log rho in terms of the this small quantity rho minus 1. Then substituting this, you get this one up to the linear order in rho. But you can also look at this expression that the trace of rho square is so-called purity, where how this reduced density matrix is close to the pure state. In the pure state case, rho square go back to the rho, and therefore trace rho is 1, so this quantity is 0. So this expression shows you that if the reduced density matrix is still in a pure state, the entropy is 0, and that is actually the condition that there is no correlation between these two. But in general, if there is some quantum entanglement, the reduced density matrix can be a mixed state, even though you start from the pure state in the full Hilbert space. Then this quantity actually measures how this reduced density matrix is far from the pure state limit, or in other words, how strongly this state A and B are entangled with each other. So this quantity will be used in the following. But you can just use this two spin state example to check how these linear and von Neumann entropy behave as a function of this linear combination. So from the it is known that if the state is a product state, namely just you combine the, for instance, up spin and down spin for particle A and particle B, then there is no entanglement between these two particles. So in that case, both entropy should go to zero. And the maximally entangled state is sometimes called the Bell state in the two spin one half system. And there are actually four Bell states, but there are two which correspond to the spin singlet, the spin triplet combination, namely the half and half mixing of the up-down and down-up component through this combination. And in this case, it is known that this entropy should be maximum, or the entanglement between these two spins are maximized. So here I show, because these are the linear combination of anyway up-down and down-up components, we consider some linear combination with a mixing angle theta, and plotting these entropies as a function of this theta. Then you see that in the limit of theta 0 or theta equal pi divided by 2, in this case, you have like a up-down the product state limit or down-up the second component limit. And in this case, both this is the linear entropy, this is the von Neumann entropy, and both becomes 0. And if it goes away from this product state limit, then you have some linear combination between these two components, and that induces some entropy, and it maximizes at the point where this theta is pi over 4 or 3 pi over 4, which is nothing but this Bell state limit. And in this case, you see that the entropy is maximized. So now you see that in both cases, both entropies can characterize this entangling nature, and its ordering is actually conserved in either von Neumann or linear entropy. In the following, we calculate this linear entropy to characterize the quantum entanglement between these two particles. Now, the entanglement entropy can characterize the entangling nature in a state. But we are considering some dynamical aspect of the quantum scattering, which is expressed by the operator or the S matrix. So we are also interested in the entanglement nature of operator, not the state. And there's this entanglement power definition, which is the property of some operator, not the state, and to characterize the entangled generation nature of that operator. Now, the definition is given here. Let me explain one by one. So we start from some initial state as a product state, namely psi A cross psi B. So any state can, which is written in terms of this A cross B structure, this is the product state. Therefore, its entanglement entropy is always 0. So in a sense, we choose the initial state to be a 0 entanglement state and apply the operator that you want to study, namely S matrix or some other operators. And then in that case, this operator changes this initial state to some different state. And this different state may have some entanglement nature, even though the initial state is 0 entangled when this operator actually generates the entanglement. So you can measure the entanglement entropy of the state after applying this operator, which is in the scattering theory, it is a final state. After the scattering, the entropy may be changed from the initial state. And this is fine. This is the nature of the how entanglement is changed by this operator. But you can, if you consider some examples, you can notice that the same operator can change the entanglement in a different way depending on the initial state. That I think I have explained in the lecture. So for instance, C not gate can generate the entanglement from 0 to maximum, or it changes from maximum to 0, or it doesn't change any 0 to 0, depending on the different initial state. So it cannot be said that some operator is generating entanglement or some operator reducing entanglement because it depends on the initial state. But we can make some state-independent nature of this operator itself by taking the average over the initial state. Namely, you pick up many different initial states, all possible initial states. Then in some cases, it generates an entanglement. In some cases, it does not. But by averaging over this, we can check the averaged property, average generation of this entanglement of this operator, which, because after averaging over the initial state, it does not depend on the initial state. So we can say that this is the ability of this operator itself. It's the nature of the operator itself to generate some entanglement. So this averaging procedure is taken by parameterizing a single Hilbert space state, namely spin state, by some invariant measure. And in the spin 1/2 case, you can use the so-called Bloch sphere. But for later applications, we utilize the so-called Fubini study measure that is known as parameterizing any vector or rates in a complex vector space, which is the CP n-1 state, parameterizing several real angles. And in the spin 1/2 case, this is a two-component vector, but you have some normalization condition and some phase redundancy. By dividing this component, you have a complex projected space of dimension 1, which can be parameterized by two angles, theta 1 and nu 1. And with this invariant measure, you can make a calculation, you can parameterize one state by using this two angles, and averaging over these angles, you can have all possible direction. In fact, in the spin 1/2 case, these two angles have one-to-one correspondence with the Bloch sphere parameterization, which actually express the direction of this spin 1/2 vector in a three-dimensional space. So it like a polar coordinate, angle component of the polar coordinate in a three-dimensional space for all possible solid angles. So in a sense, in a spin 1/2 case, this averaging procedure is to picking up any different direction of the spin A and spin B. One spin up to the other spin up, one spin up to the other spin down. But not only this, one spin up and one spin on the x direction, or any other points which is characterized by these angles. So we are somehow averaging over the initial spin direction. Then you can calculate the entanglement power as a state-independent quantity. Now we are ready to discuss the spin entanglement structure in the two-nucleon scattering. But for that purpose, we have to prepare the S matrix for the two-nucleon scattering or proton-neutron scattering in this case. And in the low energy, we have the S-wave component, and this scattering can be characterized by two phase shifts, delta 0 and delta 1, corresponding to the spin 0 component and spin 1 component. And note that the isospin should be taken automatically, determined by the Pauli principle. If you have spin 0, it should be isospin 1, spin 1, it should be isospin 0 or something. So it does not need to specify it. But in the spin 0 component, you have to project the possible initial state to a spin 0 combination that can be given by this operator. Sigma A dot sigma B is an operator that acts on the spin of the two nucleon spin A and spin B. And this combination actually projects the states into the spin 0, while this combination given a spin 1 component. So it is actually the 4x4 matrix coming from this product structure. And for that, we can apply the previous entanglement power calculation. So the S matrix is a matrix, and it is parameterized by the phase shift or given energy, and it is acting on the spin space. The result of the entanglement power by averaging over the previous procedure, you end up with this expression. So after averaging over, this is just a number, but this operator contains two parameters, delta 0 and delta 1, the phase shift, so it appears in the final expression. Now, one thing you can notice is that this is a sine square of some real quantity, so it is always positive and larger than 0. So the minimum of this entanglement power, because we are interested in minimizing the entanglement suppression, which is this power is 0. And by looking at this sine square of this quantity, you notice that there are two kind of possibilities that satisfies this phase shift relation to obtain the zero entanglement power of this S matrix. One thing is, one result is easy. When delta 0 equals delta 1, then this disappears, so sine 0 is always 0. So if the two phase shift in the spin 0 and spin 1 are equal with each other, then this S matrix doesn't generate any entanglement. But this is nothing but a spin flavor SU4 symmetry, because the originally spin 0 and spin 1 can be different. They are independent, and that's why we have two different phase shift. But to obtain this condition, this result, we have to enforce these two angles, the two phases must be equal. And this is the consequence of the SU4 symmetry. The other possibility is that some half pi difference from the phase shift to delta 0 and delta 1. Namely, if one of the channels phase shift is 0, the other component goes to pi half, or the other way around. And of course, it not necessarily be one component is 0. But if you go to the low energy limit, namely at the threshold, usually the phase shift should go to 0. Otherwise, it somehow contradicting. And the only expression is that the scattering length diverges, namely the unitary limit case. The phase shift can be finite, or in fact it can become pi half. So in the very low energy limit, only 0 pi half or pi half 0 combination remains. And this actually explains if the large scattering length result, namely the non-relativistic conformal symmetry. So we have noticed that this SU4 symmetry or conformal symmetry was the emergent symmetry in the two nuclear interaction. And in this entanglement suppression, namely, if this symmetry is realized, symmetries are realized, then we notice that this S matrix of the two nucleon scattering doesn't produce any entanglement. So the entanglement suppression and this emergent symmetry can be related with each other. So this figure schematically shows you that the entanglement power for a given, this is the low energy coupling constant or low energy coefficient in the two nucleon scattering in the spin 1 and spin 0 component. You can naively consider this is the interaction strength of the spin 1 and the spin 0. And the 0 corresponds to the no interaction, namely no interacting limit. And this quantity is normalized as a 1. This 1 corresponds to the largest interaction, namely the unitary limit. And this plot gives you how the entanglement power appears for a given set of the coupling constant. And you see that the small entanglement generation is realized in this diagonal line, as well as the 4 point on the corner corresponding to this limit. The C4 is spin 0 and spin 1 has some identical structure that is given by this diagonal line. And these 4 points correspond to these 4 corners. One of the channels has 0 interaction, the other channel is the largest interaction, and so forth. So now you see that this entanglement actually suppressed in this actually calculation. And this result that we obtain two solutions, and these two solutions are somehow interpreted using the language of the quantum information. From the result, we can notice that in order to get entanglement power is 0, this S matrix operator should have some property like this, namely it changes the product state into a product state. The definition of the entanglement power is given by starting from the product state as the initial state and measuring the averaging over the final state entanglement. And yes, because the average after averaging over all final state, it still remains zero, means that it should be always zero for any initial and final state. And the zero entanglement is only given by the product state. Therefore, for this operator, any initial product state should be mapped onto the final state, which is still in the product state. So if this is satisfied, then you can have this IES equals zero condition. In fact, the two solutions actually satisfy this result. Namely, if the delta 0 and delta 1, the difference is 0, which corresponds to the SU4 symmetry, or delta 0 equal delta 1 limit, the S matrix can be, because there are two phase shifts, but they are the same, so you can factorize. So the spin structure of the S matrix is proportional to the sum of the projection operators, spin 0 projection and spin 1 projection. And because of the projection nature, it ends up with the identity operator, which do nothing in a spin structure. Therefore, this gives you, starting from the psi A cross psi B, the final state is psi A cross psi B. This is actually a trivial one, but it is called the identity quantum gate. The other solution is a non-trivial effect. So it does nothing. So in the spin structure, it does not change its identity operator. The other solution, the half-pi difference between two phase shifts, actually do something, but still preserves the product nature of the state. And it is actually called the swap gate. In this half-pi difference case, after factorizing the common phase between these two components, you have one negative sign somewhere because of this half-pi. Exponential 2i delta is a phase shift. So its delta is multiplied 2, so you have a minus sign. And in this case, you have this combination. The sigma dot sigma doesn't disappear, but this operator is actually known as a spin exchange operator in nuclear physics, which changes a spin A cross spin B to a spin B cross spin A. So A and B are exchanged, but still the state is in the product state. And that's why this operator in quantum information theory is called the swap gate, swap quantum gate, which actually exchanges A cross B to a B cross A. And it has been known for this spin 1/2, two spin 1/2 systems. These two operators, namely the identity gate and the swap gate, are the only operators that gives a minimal entanglement, namely zero entanglement power. This can be mathematically shown. So far we have talked about the two nucleon scattering, and there are some other consequences of the some hadron scattering, not only in the two nucleon scattering, but also some other systems. The naive generalization of two nucleon scattering is to go to the three flavor, namely two nucleons is up and down quark system, but you have some strange quark. So in the three flavor case, you have octet baryon as a ground state. So you have 8 state in the baryon system. And in this baryon scattering, the three flavors, the symmetry is actually not identical to the Rajency and the entanglement suppression. Before, probably it is better that recalling that SU4 symmetry, SU4 spin flavor symmetry in the two nucleon scattering is of course obtained by entanglement suppression, but as I briefly mentioned, it can also be obtained by Rajency. So in that aspect, the Rajency and entanglement suppression give some identical result for two nucleon scattering system. But if you go to the three flavors, the symmetry is actually different. In the flavor case, the Rajency limit explains the SU6 symmetry, spin flavor symmetry, while from the entanglement suppression, as discussed in these papers, it gives you the SU16 symmetry. It is the larger symmetry, which means a stronger constraint on the structure of baryon-baryon interaction. In essence, the difference comes from the fundamental representation of the quarks and baryons, because the original regency QCD spin flavor symmetry actually comes from the quark level spin flavor symmetry, while the entanglement suppression idea directly deals with the hadron state or baryon state. So it does not go to the UDS system, but in the baryon octet system. Therefore, spin flavor combination is different. In the quark level, it is the 3 flavors and 2 spins. So it multiplying, you get a number 6, which is given by the up quark, up spin, up quark, down spin, down quark, up spin, and so on. So for this 3 times 2 structure, it's given as a 6. But you have 8 baryons, octet baryons in the baryon sector. And each baryon, like n up and down, you have 2 spin components. So you have 16 degrees of freedom in the baryon spin flavor. And in fact, some lattice QCD evaluation of some low energy structure of the SU3 baryon scattering somehow favors this SU16 symmetry that gives you some confidence on the entanglement suppression idea rather than the regency limit. Another example is that the momentum dependence on the entanglement power. So we have shown that the entanglement power is given by the difference of the phase shift. And in fact, phase shift is a function of the momentum or function of the energy. So depending on the different energy, you have some different result. And in the previous discussion, we focused on the low energy limit where the scattering length only matters. But in general, you can consider the momentum dependence. So each momentum, we have some entanglement phase shift of the 2 neutron scattering. So from this 2 neutron scattering phase shift, you can calculate the entanglement power by measuring the difference between 2 phase shift. And in fact, in the original paper also, this entanglement power of the proton-neutron scattering is calculated like this from the phenomenological 2 nuclear interactions. And well, it has some structure, but it stays at most 0.15 or something, smaller than 0.2. And this linear entropy, the maximum value is 0.5, which is the maximal entanglement state. So compared with that 0.5, this number is still small. That is for the case of the neutron-proton scattering. Now you can also consider lambda-proton scattering. In the lambda-proton scattering case, there are several known interactions, the phenomenological interactions, and so chirally effective field theory interactions. And in lambda, lambda is a baryon including 1 strand quark. And lambda proton scattering also has a spin 0 and spin 1. And so the phase shift is calculated as a function of the center of mass momentum. And therefore, we can calculate this entanglement power for a given momentum. And by using different input of the 2 lambda nucleon interaction, then the entanglement power is evaluated like this, which is much smaller still, much more smaller than the 2 nucleon force. And also, the entanglement power is in the low energy region is somehow suppressed in the hyperonucleon interactions. So in that way, we see that several evidence that in the physical baryon-baryon scattering system, the experimental data somehow shows the evidence of the entanglement suppression for the baryon-baryon scattering S matrix. So let me summarize the discussion so far. We show that the entanglement power can be defined for the scattering S matrix of baryon-baryon scattering. Its meaning is the ability of this scattering S matrix or the scattering process, hadron interaction, to generate the entanglement of the state. And this is defined like this. So you start from the product state, apply this S matrix, measure the entanglement, and average over the all possible initial state. In that way, you obtain the entanglement power. Now, the idea of entanglement suppression is to require this condition, ES goes to 0. And by applying this one to the 2 nucleon scattering, we obtain 2 symmetries, 2 solutions for symmetries. One is a spin flavor SU4, where the S matrix is proportional to the identity operator in the spin space. And the other is a non-relativity conformal symmetry, where this matrix is proportional to the swap quantum gate. These results have been already discussed in these papers. Now, from now on, let us talk about its generalization, further generalization to the Freybeis 3, and the spin is also changed from 1/2 to the 3/2, which is related to the spin decuplet baryons. So first, let me remind you what are the decuplet baryons. A decuplet is a 10 representation of SU3 appearing in the baryon ground state together with the octet. So here it is a wet diagram of the baryon decuplet, which forms this triangle shape. The top part with the smallest, largest hypercharge is the delta particle, delta plus plus, appearing in the pioneutron scattering. And this sigma star, there are also ground state sigma in the octet channel, and sigma excited state, sigma star xi excited state, xi star. And this is the omega particle, which was predicted by Gell-Mann by using this equal spacing, mass spacing law, using SU3 symmetry. And then it was observed later on to get to with which the Gell-Mann received this Nobel Prize for prediction of this omega particle. This is a 3s quark state, SSS state with a negative charge. And because of the symmetry of the hadron, because this delta plus plus is actually given by UUU, or this omega is SSS, the spin is also combined with the spin 3/2 system. There are 3 baryons, and 3 quarks in the baryons, and 1 quark has spin 1/2. So the 3 quark system can have spin either 1/2 or 3/2. And this state, the decuplet should be combined with the spin 3/2 in order to satisfy the totally antisymmetric condition for the baryon wave functions. So anyway, these states are known, and it is next to the ground state of the octet baryons containing the proton and neutron. So there are some phenomenological reasons why we are interested in the scattering between these decuplet spin 3/2 baryons. One is that there are some channels where people discuss the possible large scattering length nature of two decuplet baryons. Remember that the non-relativistic conformal symmetry appears from the entanglement suppression, and it is actually a good combination with this large scattering length, because this result may be explained from the entanglement suppression idea. Now, one example is actually this 2 delta particle, delta state, where some people discuss that there exists some state near this delta threshold, sometimes called D star. It's originally predicted by Freeman Dyson and collaborator in many years ago, based on, actually this is also spin flavor symmetry's consequence. But some recent experiments suggest that there actually exists some state near the threshold. So the existence of some bound state near the threshold actually induces the large scattering length, as in the case of the deuteron in the 2-nucleon scattering. So this delta-delta system, even though it is different from the nuclear force, it may have this large scattering length, and it can be related to the entanglement nature of this baryon scattering. Another example is actually our main focus, which is the omega-omega system, the 2 omega particle. And there is no experimental data because it contains many strange quarks. You need a 6 strange quark, which is rather difficult to produce in the experiment. But recently now the lattice QCD can be performed directly for this hadron system with a multi-strangeness system. And HAL QCD collaboration actually calculated the potential of this omega-omega system, and which gives us the scattering length is of about 5 femtometer, as large as the deuteron case in the 2-nucleon scattering. And in fact, there is a shallow bound state of about a few MeV in the omega-omega system. Therefore, this system looks very similar to the two-nucleon system in the deuteron channel. And therefore, this nature may also be related to the relativistic conformal symmetry induced by the entanglement suppression. So this is the hadron physics motivation to study the scattering of decuplet baryons. From the viewpoint of the quantum information, this spin 3/2 nature is also interesting. Because we mentioned that spin 1/2 is the standard qubit, a quantum bit, but spin 3/2 we have a 4 component, plus 3/2, plus 1/2, minus 1/2, and minus 3/2. So it is a 4-dimensional system for a single state, sometimes called a 4-dimensional quantum qubit. The 3 component is called the qubit. And more than 4 component is generally called the qubit, a 4D or 5D or 6D or something. So this spin 3/2 system, considering the scattering of the spin 3/2 system, is equivalent to discuss the quantum system composed of the 4-dimensional qubit system. And its symmetrics correspond to the quantum gates for 4D qubit systems. Now, the first we have to parameterize this spin 3/2 system. As I mentioned, this has a 4 component rather than the 2 component of the spin 1/2, and it should be parameterized by the 4 complex vector, 4 complex numbers. But the one normalization and the phase redundancy has to be removed, and this is given by CP3. So it can be parameterized by 6 angles, 3 theta and 3 nu. The structure looks a bit complicated, but if you, for instance, neglect this phase part, this is a combination of the cosine and the sine, and it is actually the 4-dimensional Euclidean space, the polar coordinate in the 4-dimensional Euclidean space. Therefore, this can be parameterized the real part of these 4 components concisely with a unit normalized vector. But in this case, we are dealing with the complex vector. So we have to put some relative phase to take this complex nature of this vector. But for this relative phase, we only need a 3, because the total phase of this all component is redundant because of this complex nature. So without loss of generality, you can take the 1 component as a real vector. So only have a 3 relative phase relative to this first component. So in that way, we can parameterize 6 angles anyway. And the invariant measure is also known to have this integration. So what we need to do is to consider the symmetrics of the spin 3/2 system and calculate the entanglement power, as in the case of the spin 1/2 nucleons. But there are some more complications, because in the spin 3/2 case, the combining 2 spin 3/2 state, the total spin can be 0, 1, 2, and 3. And 0 and 2 are the anti-symmetric combination with respect to the interchange between 2 particle A and particle B. And 1 and 3 component, spin 1 and spin 3, are the symmetric component. So in contrast to the spin 1/2 case, there are only 1 antisymmetric, 1 symmetric component. We have actually the 4 component. And therefore, the S matrix also contains 4 distinct states, sectors, each sector containing the 1 phase shift. So spin 0 phase shift with the spin 0 projection, spin 1 phase shift to spin 1 projection, spin 2, and spin 3. Now, the spin projection operator becomes a bit more complicated. It's essentially a generalization of the 1 and the sigma dot sigma structure. But because of these 4 eigenvalues, we have to consider up to the cubic order of this sigma dot sigma structure. And in a way, just by doing some group theory, you can calculate all the structure of this spin projection. So it is actually the generalization of the nucleon-nucleon scattering. So what we need is to calculate the entanglement power of this operator by averaging over these angles. But now you can see that these angles become more complicated. In the spin 1/2 case, we have only 2 angles for each spin. So we need 4 integrations in total. But in this case, we have a 6 for each component, meaning that a 12 integration is needed. And also the spin, this matrix is a 4 by 4. Therefore, the product system of the spin A and spin B, we have a 16 times 16 matrix, which is much larger than the 4 by 4 in spin 1 half case. Anyway, you can put these all combination into the mathematical and wait for, let's say, 3 days. Then the result is obtained like this. It's very complicated, but the point is that the entanglement power is given by some cosine of the phase shift difference, where the combination of the phase shift can be different from 0, 1, 2, 3, and so this kind of structure with some specific coefficients. It's a bit complicated, but the basic structure you can see is that some constant term is a positive sign, and all the others are some negative coefficient times cosine of the phase shift difference. And if you carefully count all these numbers, this constant is equal to the sum of all these coefficients in front of the cosine term. In other words, if and only if all cosine terms becomes +1, then this constant minus all these terms cancelled with each other, which gives you the entanglement power is 0. So in order to satisfy ES equals 0, you have to take this cosine is +1, this cosine +1, this cosine +1, and this cosine +1, and so on, so forth. Okay? And by carefully looking at all these structures, you will notice that these two are the solutions that gives us the 0 entanglement generation in the spin 3 half case. Namely, in all cases, delta 0 and delta 2 must be always equal. I think this may be taken from this one because the 2, rather than 4, there are only 2 terms here. So in that case, you have to consider this difference should be only pi, which means that these are basically equal, and delta 1 and delta 3 must be also equal. And there are so we define these 0 and 2 as an even spin phase shift because they are equal. So there's 1 degree of freedom. 1 and 3 define the odd power phase shift, odd spin phase shift. And the relation between even and odd is given by 2 possibilities again, where the even and the odd has no difference, which means that all 4 phase shifts are equal, and this corresponds to the identity gate I will explain in the next slide. And you can also have this half pi difference between even and odd, and this will correspond to the swap gate. So anyway, although the structure looks a bit complicated, but the final result looks also similar to the case of the nuclear force. Let's see whether this is actually correspond to the identity or swap. In this case, it is actually clear because in the all phase shifts are equal, as in the case of the nuclear force, you can factorize all the phase shifts because in spin 0, 1, 2, 3, every asymmetric element has the same structure, same phase shift, so you can factorize this out. Then the spin structure of this S matrix is given by the sum of all projection operators from 0, 1, 2, 3. And by definition, by summing up all the projection operators, it goes back to the identity operator. So in the identity, so this is in spin state, it is the identity gate. It maps the original product state into the final product state, and therefore this doesn't generate the entanglement, as in the case of the nuclear. The other example is the swap gate, the half pi difference. As before, we have some minus sign after factorizing the trivial phase. And this combination actually can be written like this form, namely, the projection operator can be decomposed into the projection of the symmetric component, in this case 1 and 3, and the anti-symmetric component, in this case 0 and 2, where symmetric and anti-symmetric correspond to the symmetry between under the exchange of the 2 particles. As I mentioned, this even spin anti-symmetric and odd spin asymmetric. So in the swap gate case, the spin structure of the matrix is not identity, but it is some combination of the sum of the symmetric projection minus the sum of the anti-symmetric projection. And with this, you can generally show that even though you have many components, this combination always gives you the swap together. This has been explained in our paper. And therefore, we see that in the spin 3-half case, actually, as in the case of the nuclear force, we have two solutions, identity gate and swap gate. And from some fancy mathematics, it can be shown that in the same dimension bipartite system, the minimal entangler, namely zero entanglement power operator, there are only two operators, which can be reduced to the identity and swap gate, even for any dimension. So in our present examples, we have shown that the identity and swap exist in the spin 3-half system, but in more general discussion in the mathematics, you can also show that this structure, these are the only structure that we can obtain the zero entanglement. And it can be, we can check. Now, for the moment, we didn't talk about the flavor structure of this decuplet baryon, then focusing on the spin structure. And this is fine. Now, we have to combine this result of the spin together with the flavor. And in the flavor, it also becomes a more general, larger space because in the spin, as I said, spin is a 3-half in the single decuplet baryon. So we consider this a product. In the flavor, this is a decuplet, so 10-dimensional representation with flavor SU3. So the two baryon system consists of, can be expressed by the 10 times 10. Whose irreducible decomposition gives you 27, 28 anti-decuplet and 35. And this 27 and 28 is known to be asymmetric under the exchange of a particle A and B, and 10 bar and 35 is anti-symmetric. And as before, in the S-wave scattering, we have to combine the anti-symmetric spin and the symmetric flavor, or anti-symmetric symmetric spin and anti-symmetric flavor. So you have 4 choices for each combination. So altogether, we have 8 different phase shift for the decuplet scattering. Namely, this is a spin. So spin 0, flavor 27, spin 0, flavor 28, which is given by this combination, and spin 1, in this case, you have to combine like this, so 10 bar 35, and so on and so forth. So up to here, we have 8 independent phase shift under the two crosses symmetry. The S matrix can be formally written in this form. So we first project in the spin space into the spin 0. But in that case, the flavor is not unique. You still have two possibilities, 27 or 28. So you further apply the flavor projection, flavor 27 projection, flavor 28 projection. And after spin 0, flavor 27 projections, the phase shift or the S matrix is related to the spin 0 flavor 27 component. So you have some S matrix structure here. In the same way, we have spin and flavor projection. We have 8 different spin flavor combinations. And by considering this structure again, I skip all the details, but zero entropy, zero entanglement power is achieved if this condition is satisfied. Namely, this is also basically the same as before. And now we have different flavors, but even though we have different flavors, they should be equal with each other, or if the spins are the same. So we define the even spin phase shift. For the phase shift of spin 0 or spin 2, whatever the flavor is. Also, all the spin phase shift is given by spin 1 and spin 3, again, whatever the flavor is. So there are only 2 degrees of freedom, and the relation is also given by 0 or half by difference. So in order to look at the emergent symmetries, it is rather easy to utilize the effective Lagrangian, the effective field theory approach in the low energy limit. That is actually also related to the effective field theory that we introduced in the non-relativistic scattering of the particle system. To describe the baryon field, so one baryon contains a flavor indices, which is expressed by the vector in the flavor space, while the spin is expressed by the suffix I, where I runs from 1 to 4, representing the plus 3 half, plus 1 half, minus 1 half, minus 3 half, and so on. So the effective Lagrangian, which produces the same phase shift for all channels. So it is even minus or equal 0 result, which means that although there are 8 independent phase shifts, all they should be the same because they are already classified into two categories, even spin and odd spin. And this condition gives you all this even and odd are also the same. Which means that all the phase shift, all the 8 phase shifts are equal with each other. And that interaction is given by this form, which is actually T state contains a 10 decuplet baryon flavor representation as well as I. So this is actually the inner product of the spin space as well as the flavor space. And this is given by some one constant. That is the Lagrangian that can give us this result. And this one is the 10 flavor indices. And for each 10 flavor indices, we have 4 spin indices. So if you write this state in terms of the 14 component spin flavor vector, delta plus plus and spin plus plus, and so on and so forth. This one is just the inner product of the very big 40 times 40 vector, 40 column vector and 40 row vector as an inner product, which is invariant under the norm conserving rotation, namely SU40 rotation, the 14 component vector rotation in the complex space is symmetry that gives us this phase shift relation. So now we have the SU40 spin flavor symmetry, very large symmetry. And the half-pi different case, it needs some more explanation, but we can actually write down the effective Lagrangian, which contains the two components. One is the same structure, T I dot Ti, which is this part itself is invariant under this S40. The second term is a bit different. Although it looks at T dot T and T dot T in the same way, the spin combination is not as equal with this one. This square means that Ti dot Ti times Tj dot Tj, the summing of the spin is taken in the same with the flavor. But in this combination, T dot T, T dot T, so the flavor indices is contracted with this combination, but spin indices are contracted with this part and this part, as well as this part, this particle, and this particle. So that's different from this. And in order to have the symmetry of the symmetry operation that preserves this interaction Lagrangian structure, the IC40 is not symmetry because it violates. It is broken by this term. But still, we have the spin SU4 and spin 10. Spin SU4 and the flavor SU10 that produces this. So essentially, it is an inner product. So it has no, in the Lorentz sense, it is a scalar. So this has no flavor and spin. This is under the rotation of the 10-dimensional or 4-dimensional each space. But in this case, I didn't mention very clearly, but this half-pi difference also again induces some non-relativistic conformal symmetry. So in the decuplet baryon scattering, the identity operator gives us the SU40 spin flavor symmetry, while the swap gate operator gives us the spin SU4 times flavor SU10, and also non-relativistic conformal symmetry. So it's a large symmetry. Here I just explain this SU40 or SU4 times SU10 structure can be naively obtained by counting the independent degrees of freedom. This is a kind of hand-waving argument, but still, actually, we can make a confirmation of the previous symmetry result by looking at the number of independent particles. Now we have two sectors, spin even, spin 0 or spin 2, and spin odd, spin 1 or spin 3. And in that case, the combination of the flavor should be 27 or 28, in this case, and 10 bar and 35. So let's count if there is a symmetry, namely, we always have this even spin and odd spin, irrespective of the flavor, are independent. Namely, although there are 8 phase shifts, we effectively only have two phase shifts, delta even and delta odd, which means that all these combinations, spin 0 and spin 2, and also flavor 27 and 28, any combinations, we have the same result. So we have a very large multiplet containing all these possible structures. So let's count how many states that we have in this both even, delta even part and delta odd part. Now spin. Spin 0 has a spin singlet, so there is only one component. Spin 2, you have a +2, +1, 0, -2, -1, and -2, which has a 5. So altogether, the spin degrees of freedom is a 6 for each flavor component. Now, flavor 27 and 28, you just add up all these two. By the way, 27 means that in the these two baryon systems, you have a 27 different combination like a delta plus plus, delta plus, delta omega, and so on. So the combination of two baryons, there are 27 combinations that form some flavor representations. So in the same way, 28 contains 28 components. So by summing up these two, we have a 55 degrees of freedom in terms of the flavor. And spin and flavor are independent. They are the outer product state. Each flavor state, like a delta omega, you can have a 6 different spin components of each spin combination. So we have to multiply these two to get a total number of spin flavor state of the two baryon system. So 6 times 55 gives you 330. In the same way, we can calculate spin 1 is a 3, spin 3 has a 7 component. So there are 10 spin components. The number of flavor degrees of freedom is 45. So multiplying this, we have a 450 degrees of freedom. And altogether, we have a 780. And this number actually corresponds to the spin flavor SU40 multiplet. So in the SU40 group, the fundamental representation is a 40. Although it's a big number, it is a fundamental. So we have to consider 40 times 40 decomposition. It's actually fundamental times fundamental, and you can decompose 820 and 780. And if sorry, this is a case of the identity gate. So all these two structures should be the same, namely altogether 780 different baryon spin flavor combination has the same structure. So the some multiplet appearing in the two baryon system in the following the SU40 symmetry should contain some multiplet which contains exactly this number. Now, suppose that you have this fundamental representation 40 and multiplying two 40s, namely one baryon and another baryon under this 40 symmetry, you have these two combinations, 820 and 780, and this number exactly corresponds to this, which means that this all decuplet baryon scattering this different combination can be summarized into this one of the multiplets appearing in the SU40 symmetry. And in fact, this one actually gives a desired symmetry property between the exchange of the two particles. Now in the swap gate case, we have to independently realize these symmetries, namely SU4 spin and SU10 flavor. So the spin part, you can consider these two. So spin SU4, under the spin SU4, the fundamental representation is a 4. So 4 times 4 can be decomposed into the 10 plus 6 in the SU4. And this number 10 corresponds to the 10 independent degrees of freedom in the delta odd case. Notice that in this case we have some difference. So delta even is not exactly same with the delta odd, which means that this sector and this sector are independently satisfying the same properties. So this spin 10 corresponds to the number 10 appearing here. That corresponds to the odd spin component, and this 6 representation corresponds to the spin 6. So actually, the SU4 spin symmetry have a two multiplet containing 10 members and 6 members that can explain this 10 in the spin odd component and 6 in the spin even component. You can do the same thing in SU10 decomposition. 10 times 10 is a 55 plus 45, exactly corresponding to these two numbers. So this is just a steric confirmation, but you can see that actually the SU4 cross SU10 flavor symmetry has some sufficient representation that has the spin and flavor symmetry structures appeared in these two cases. And more direct confirmation of this symmetry nature is coming from the effective Lagrangian that we have seen before. So before closing, let me briefly talk about this omega-omega system. Of course, it is included in this general SU40 argument, but by picking up this component itself is also interesting. Because in the omega-omega case, the flavor degrees of freedom is somehow frozen. Namely, of course, under the SU3 it changes, but the strangeness is preserved in the strong interaction. Therefore, omega-omega has no coupled channels. It cannot go to the different channels, and it is a single channel probe. And omega are the same particle. So it is like in the two neutron case, the neutron-neutron scattering is the identical particle scattering. So just in the same way, omega-omega is the identical particle scattering in a decuplet sector. And in this case, because there is no flavor degrees of freedom, you have only spin wave functions, and spin wave function must be anti-symmetric under the exchange between two particles. And with this consideration, the two neutron scattering, for instance, is given by this operator. Namely, in general, we have a spin 0 and a spin 1 in the two neutron system. But if we pick up a two neutron charge 0 component, you only have this one, spin 0 projection times the phase shift of spin 0. Namely, spin 1 is absent, even though even the projection operator is absent. Now, omega-omega case, we have 0 to 3, but this requirement for anti-symmetricity for the fermionic nature, we only have a spin 0 phase shift and spin 2 phase shift. Namely, spin 1 and spin 3 doesn't appear here. The problem is that there are some sort of problem in evaluating the entanglement power for this kind of identical particle systems, because the S matrix is not a unitary operator in the full Hilbert space of psi in. In other words, unitary means that SS dagger is 1, the identity operator. But if you consider SS dagger of this operator, the phase part cancels, but J0, the projection operator is a self-adjoint, so it is the dagger is a J0 and J0 square is a J0. Which means that this operator, this SS dagger combination of the two neutron scattering, we get the spin 0 projection. Actually, in this system, this is not identity, because the identity is given by the spin 0 plus spin 1 projection. Okay, so it reduces some space. The essence is like schematically expressed in this form. So because this anti-symmetric and the symmetric component are somehow decoupled in the structure of the S matrix, this is some block diagonal structures. So the anti-symmetric, namely spin 0 component and the spin 1 symmetric component of the two neutron scattering is somehow decoupled. In the proton-neutron scattering case, we have both components that have some influence on the entanglement power. But in the two neutron scattering, because we only have the spin 0 projection here, which is schematically in this case written like this form, so we only pick up this antisymmetric component. Then the its matrix is not unitary. Or in other words, if you restrict yourself into the antisymmetric Hilbert space, then it is the identity operator. Or in other words, this J0 is the identity operator in the antisymmetric space, but not in the full Hilbert space, including the symmetric one. The problem of this appearance of this reduced Hilbert space structure is that the density matrix is not properly normalized. Namely, we consider the density matrix from the outgoing state, which is given by the multiplying the S matrix to the initial state. And considering the trace of this operator, this S dagger S is now not the identity, but is a spin 0 projection. So this is essentially the expectation value of this spin 0 projection operator from the initial state. And if your initial state is with all living in this antisymmetric sector, then this gives you 1, because as I mentioned, J0 is the identity operator in the antisymmetric space. But if you consider psi in the full Hilbert space, which is needed in the calculation of the entanglement power, because in the entanglement power, we pick up the product state as the initial state, and the product state is not a good quantum number. It has no good quantum number of the spin, namely, it is not the eigenstate of the total spin in general. Therefore, it cannot be considered as either antisymmetric or symmetric. It's actually a linear combination. So in the calculation of the entanglement power, we encounter this kind of problem, namely one of the initial state is not properly normalized in the trace. So we need some additional normalization condition for realizing the entanglement power. And this is essentially known in many textbooks. So if this is not normalized, then you have to give this normalization factor in the density matrix. In general, this is okay. But in practice, this may introduce a bit more complicated calculation if we, for instance, integrating over this component in the calculation. So to avoid this, we introduce a k-weighted normalized entanglement power. Namely, we multiply this case power before taking the average of this operator and normalize this operator by this form. The point here is that this, if there is, depending on the power of k, you have some different weight to make a normalization of this operator, the density matrix. But if you, it by the way can be shown that for two neutron scattering case, it is expected that the entanglement power should be 1/2, because it originally started from the product state. But applying this two neutron operator, it always projects the spin state to a spin singlet, which is a maximally entangled state. And it is in the linear entropy, it becomes 1/2. So any initial spin configuration, which is a product state, after multiplying this operator, it should always give you 1/2. So if you do not make this kind of normalization, you don't get the correct result of the 1/2. That is why we have to introduce this system. And in fact, we can check that we can analytically show that this result, this 1/2 for the two neutron scattering is dependent on the value of k of this prescription. And once you check this, it is actually particularly easy to calculate this k equal 2 case, because the integration of the numerator and denominator somehow decoupled. And this normalization to the reduced, this normalized density matrix times this factor reduce it to the original calculation of the entanglement power. So in this case, you can perform the same calculation as before, but just apply some normalization to the total weight of this quantity by this expression. Anyway, it's more detailed, but one thing we want to emphasize is that for the identical particle scattering, we need some proper normalization structure. So again, the omega-omega scattering, the S matrix contains two phase shifts. Although this is identical particles, because of the larger spin structure, we have two independent components in the flavor, spin 0 and spin 2. Now, with this proper normalization, the entanglement power of this two omega-omega scattering, we can obtain this entanglement power expression. So there's only single component cosine, and as before, we can check two minimum entanglement solutions. But you notice that in the previous examples, we have some constant term minus cosine term, where the coefficient of the cosine term exactly cancels the constant term. And that's why we can obtain the S equals 0, EP equals 0 solution. While in the present case, even though the minimum is given by this, namely cosine is a +1, which gives you the largest possible subtraction from 25, this gives you not to 0, but is 24 divided by 48, which means that 1/2, as in the case of the two nucleon scattering. And this is natural because anyway we have this anti-symmetric combination in the spin component that gives you this original 1/2 coming from the identical particle scattering. But still it is a minimum component. And in the minimum case, we have two structures, which is not exactly the identity, but this is some projection to the antisymmetric space. And also, we somehow in the paper discussed that this structure coming from the half-pi difference is called, it can be regarded as some kind of swap A. This is not the original swap because there are only symmetric components. You cannot make a direct swap structure, but within this anti-symmetric spin configurations, this operator actually swapping some two states from each other. So in this way, anyway, we have the similar two solutions. And the result of the phenomenological consequence of the omega-omega scattering is that in the lattice QCD, as I mentioned, there is some indication that one of the channels are close to the unitary limit. But this information is only obtained for the spin 0 component, not for spin 2. Which means that in the spin 2 component, the interaction is not at all known. But this entanglement structure can give us some hint to the unknown spin component, namely spin 2 component, either two cases. The one case corresponding to this identity operator or the phase shift difference is 0. In that case, this means that this spin 0 and spin 2 components have similar structure, and therefore the result of the spin 2 should also be close to the unitary limit as in the case of the spin 0. This is the solution for this case. The other solution is the half-pi difference. In the half-pi difference case, if one of the state is close to the unitary limit, and the other channels must close to the 0 interaction limit, mainly almost no interaction limit. Therefore, suppose that spin 0 is from the lattice QCD, it is close to the unitary limit, then the spin 2 part is regarded as almost non-interacting. So this shows us that the spin, although we do not know at the moment, know any information on the spin 2 omega-omega scattering, to suppress the entanglement in the omega-omega scattering, this component must be behave similarly with the spin 0, either similarly with spin 0 or it has almost no interaction. That's the consequence that we can say for the spin 2 component of the omega-omega scattering. So here's a summary of this half of this talk. We generalize this argument of the entanglement suppression for the case of the baryon decuplet scattering. And in the spin 3/2 system, we can also confirm that the zero entanglement solution can be achieved by two different cases. One is the identity operator case, and the other is the swap operator case, even for spin 3-half case. And this actually related to very large spin flavor symmetries. In the identity case, we have a spin flavor SU40, and the swap case, spin SU4, flavor SU10, and the non-relativistic conformal symmetry. That's the emergent symmetries we expect for the decuplet baryon scattering. Now, if the identical particle scattering, we can say we need to make a normalization of the final state carefully. And in the omega-omega scattering case, where only one of the components is known from the lattice QCD, we can have some indication or some prediction for the spin 2 component. That will be useful for the phenomenological application of this omega-omega scattering system. Okay, that's all. This is the result for what we found in this paper.